First of all, I think we should make an introduction, brief introduction for the jury. I'm Hong Mingguang from Taiwan Normal University. And
I'm He Jinlong from Shanghai University.
Hello everyone, I'm Yan Wenlan. I'm from the National Taiwan Normal University.
Hello, good afternoon. My name is Su Jung from Jiayi University.
Hi everyone, I'm Yu Ying from Hongjiao University. Thank you.
Okay, let us introduce the reporter team. Please introduce yourself. By the way, you can see the name on the project.
I'm the captain of division from Zhanghua Girls Senior High School. My teammate Zheng Youying, Xue Bingyu, Taiwan Min, Thank you.
And then for the opponent.
Hello, the honorable judges and fellow competitors. I'm the captain from Team Excelsior. My name is Zhu Chenkai. And this is our teammates is Hou Pingxian and Wu Hanxu, Cai Yuxing, and Ling Xingyuan. Thank you.
And lastly, you are.
Hello everyone, this is Qiu Zeta from Pinghan High School. I'm Li Shenhan, and this is Li Chen Yurui, Jiang Yizhe, Yan Yizhen, and Zhu Yanxi. Thank you.
Okay, we'll start our first session. I think the opponent should challenge the reporter for one problem. All problems are available now, just for 1 minute at most. The opponent. Okay, what problem?
We want to try topic number 6, tennis ball tower.
Number 6, tennis ball tower. So, the reporter can take the time to accept or reject it, just for 1 minute. Accept it. Okay, we can start now. I think the reporter has 5 minutes to prepare for preparation. In the meantime, please write down the name of the reporter, opponent, receiver, presenter.
神神多多的，
Okay,
有点 take off the mask.
there's a three that the presenter can take off his mask, but all the others should put on the mask. Okay, 5 minutes up. I think the reporter should make a 12 minutes report. Please start.
Hello everyone, my name is Wei Han. I'm the reporter from Team Vision. Today I'm going to report to you problem number 6, tennis ball tower. So here's our problem statement. It's about investigating structural limits and stability and discussing per layer more than 3 balls. How many balls on the top is suitable? And we will mainly focus on how the static friction, normal force, work on tennis ball tower. And this is our outline observation theory, experiment and discussion conclusion. And here comes our observation. So basically, we will talk about 3 balls and the multiple structure. And as you can see that in 3 balls per layer, 4 balls, 5 balls structure, they both have symmetry and a regulation between balls according to this transparent diagram. And we found out that 3, 4, 5 balls per layer, they didn't touch each other. It's the same layer, so they won't have acting force between each other. Next, we use the easy structure to talk about the force, and here are basically the forces that we think we will happen to keep it stable. Lower force and friction. Then we'll take a detailed discussion about friction later. And next is our theory part. The static equilibrium is the theory that's used to see the structure can be stable or not when both resultant force and resultant moment equal to 0. The structure can then be built, and we will talk about some factors which affect the structure and lead to non-static equilibrium. And this formula is for thinking of the tower will form not. And Newton's third law is for the direction of static friction. As for the last one, simple harmonic motion, it is for an experiment that we'll talk about. And next, this is the face-centered closest packing. We use this structure to help us think easier about some forces in tennis ball tower. However, this tennis ball tower is not a subset of face-centered packing. In order to let us talk about the structure easier, we mark the board on top as ball 1 in the first layer, and second layer 2, 3, 4. Then third layer 5, 6, 7. Then here comes our experiment and discussion. So first of all, we'll based on structural limits to talk about our experiment. Second, we'll talk about how we define the stability, and the next one is about the suitable numbers on top for multi-ball tower. We think it is static friction because there is no relative motion between balls in this structure. And according to the experiments we do, we know that balls between layers and static friction help build the tower. And as you can see, that's when we take off ball 1, the structure scatters like a fountain, and the order of it is the second layer, third layer, fourth layer, and then down to the bottom layer. Therefore, we think that ball 1 needs to give second layer static friction to hold it, and the direction of it is inward. And then according to the Newton's third law, Second layer will also give ball 1 a static friction outward, and then same as third layer. Second layer gave a static friction to it, and also this one. So as you can see, if second layer is static equilibrium, the first layer ball 1 give should be inward, and the first layer third layer give is outward. So we have the formula here. We count the layer 1 and 2s, and 1 multiplied by cosine equals 1 divided by 3 mg, and the F1 is smaller or equal to N1 multiplied by mu s. So we have this formula. And we know that the mu s will larger or equal to this number. And also, this is the closer look to our structure. And we use this triangle to count our M1 and our F1. So, here's counts our formula. And also, we also count layer 2 and 3, layer 3 and 4, and layer 4 and 5. And interestingly, the formula of layer 1 and 2 and layer 3 and 4 is equal. But layer 2 and 3 and layer 4 and 5 formula is not the same as layer 3 and 4. And because the layer 2 only accepts the first from ball 1. But the layer 3 accepts from 2 balls from the layer 2. And the layer 4 accepts from the only 1 ball from layer 3. Yeah. And so this is our discussion. We think that the mu s will become smaller as the layer become more. And here's we count. So we know that the maximum fs will become bigger as the m become bigger. So we can think that, so we measure the static friction coefficient, and the fabric is about 1.73. Acrylic thread is about 0.4. Glass plate is 0.48. And next one, we want to know the strength between layers, so here's the diagram. If we take all three as our target, the first each gate will be like this, and after we use the principle of static equilibrium, we know that the normal force that ball 1 give is 1 divided by 3. And the friction of it is about 0.32, 1 divided 3 mg, and it makes sense. The coefficient of it is much slower than maximum static friction that we measured, because the structure doesn't need that much of friction. As for the other perspective, the friction that ball 1 give is equal to the friction that table give. This means the structure is static equilibrium. Likewise, if we take a deeper look at the friction from table, you can see that we can know the maximum static friction according to the amounts. We can know the maximum static friction according to the amounts we got. And the actual friction that the structure is just right equal to the friction between ball 1 and ball 3. And so it seems like the friction from table is passive, it just gives the friction for that structure need. So if the structure goes high, this part will biggest friction, because the range of it can be like this. But however, there are still some factors that why the structure cannot be built as high as we could, such as the fabric of the ball, the deformation variable. The fabric on tennis ball contacts will stuck together, so it will not just because of the friction. Besides, different kinds of tennis ball that we use will also affect the structural limits, and we tried the softer one and the hard one. As for the stability, we think that it is the tolerance that a tire can suffer external force and can be stable. So here's the experiment that we decide degree or inclination and vibration of the button. The degree that the tire will fall is 3 degrees for 3 layer, 2 degrees for 4 layer, and 1 for 5 layer. So we note that the higher layers require less angle to collapse. So the things we learned that is that when the tar gets higher, the center of it will also be higher, and the angle that makes it fall will be smaller. So the highest the tar is, the stable the tar will be. And next is the vibration experiment. We decided to experiment. One is fix the amplitude, change frequency, and the other one is fix the frequency, change amplitude. At first we think the amplitude will have apparent change in different layers. However, the result of it appears not. Both 3-layer and 4-layer fell down at the same amplitude, so it's kinda hard for us to segment. So we'll take the first one to talk about. So while the structure will fall when it's being through the time of vibration, and here's the diagram writes the red lines movements of both three. And you can see the blue arrow right there, it is time that both three starting to fall. So however 3 balls per layer, we needed to find ways to build the tower. The first one we tried 5 balls per layer. And we found out regulation pattern isosceles trend load is the easy structure for us to make the up a tower, and we can build the tower up to 5 layers as per 7 balls per layer. We also use isosceles trend load to build it, and we can build up 3 layers. And the regulation that we found is that if top ball number is n, every layer down below will be 2n plus 1. And here comes our conclusion. In theoretically, no structural limits, but in reality, table friction affects it. The highest the tar is, the unstable the tar will be. And odd number top n per layer, 2n plus 1. Shape is the isosceles trend load. Even number haven't found, but the shape square for both per layer. And thank you for your attention.
I think the opponents can ask 2 minutes to ask a question. Short question and short answer. Okay? Okay.
Is the friction coefficient between the ball is the main reason that caused the tower to be stable?
Yes.
And if the friction coefficient between the different layers will be the same?
No, it will not be the same.
As the normal force is proportional to the friction in every layer. Proportional means like a positive correlation.
No,
And as the tensile tower stable when it's stacked with no gap. And it is stable or not?
with no gap.
Yes, no gap means stacked closely.
Closely, I think it will not.
And in your theory, did you consider the gap between the tensile or just stacked closely?
We just let go of it, and we just know that there is some gap between it.
Okay. As the tennis ball in the same layer gives the normal force beside the tennis ball. Just in the same layer, the normal force will give the ball will give the normal force beside.
No, because there is a gap.
Okay. Did you consider the tower as a 3-dimension?
3-dimension? Yeah. Yes.
When the tennis ball tower is stacked higher, the angle between the lower layer will be increased or decreased.
Please repeat it again.
When the tennis ball tower is stacked higher, the lower layer, the angle between the lower layer will increase or decrease.
Increase.
And did you consider the deformation of the tennis ball?
Yes.
Is the friction and the normal force is the main force that causes the tennis ball tower to be stable?
Yeah.
Is the tower have the limit of its height?
Oh, yes.
And please turn to page 7.
Okay, time's up. 2 minutes up. I think the opponent can take 2 minutes for preparation. And then proceed with. Okay, the opponent can take the floor for maximum 4 minutes, and then you can start now.
Hello, honorable jurors and fellow competitor, and the opponent from Team Excelsior, opposing the problem number 6 tennis ball tower. Here's the problem statement. Build a tower by stacking tennis ball using 3 balls per layer and a single ball on top. Investigate the structural limit and the stability of such a tower. How does the situation change when more than 3 balls per layer and a suitable number of balls on the top layer are used? And the opponent wants to focus on what force made the structure to be stable. And the opponent thinks that the friction coefficient is an important factor that will affect the influence of the stability. And due to the problem statement, we want to investigate the structure of more than 3 balls per layer. The opponent believes that the structure of solving problem can separate into, first we need to analyze the force in the structure, because the friction normal force, gravitation normal force might happen in the structure, and we should consider it. And then we need to investigate the friction coefficient that affect the stability of the tower, because the friction coefficient might affect the limitation of the gap between faults. And then the minimum energy is caused by the normal force from the same layer. We also want to consider, and that is how the parameter that such as the mass of the top bolt and the friction coefficient affect the bolt and the tower. And here's the strong and weak point for the reporter. First, he has demonstrated the tennis ball tower, but he did not consider the normal force between the same layer, which opponent thinks that it should be proved, and if it proved is no normal force in the same layer, it should be accepted. And next is he separately calculate every tennis ball force. But he's too idealize the assumption for the gap between the tennis ball, because in the theory, there should be no gap between the ball. But when the reporter's observation video, there should be a gap between the balls. And she didn't consider the information. And then she measured the friction coefficient. But he cannot really demonstrate the actual force that act on the tennis ball tower. And he did not consider the boundary condition between the different layer and between tennis ball and the table. And she didn't focus on the structural limit and demonstrate in the theory. And here's the point to be discussed. And first, we need to talk about the force analysis, because the tennis ball is an object with and weight. So the opponent believes that there should be a gravitational force that will affect in the whole structure and that point downward. And second is the friction, because there is a multiple contact point in the structure. So the opponent thinks that the friction may somehow affect the contact point. And we want to know what is the actual direction and the steady friction. And then is the normal force. We want to know what is the direction of the normal force, and the normal force only not supporting gravitational force. We also want to know that the effect of the normal force in the horizontal force. And next come to the delta analysis. Because when it has a boundary condition, including the friction coefficient gap between the balls, which affected by the friction coefficient, and y is the limitation of the amount of layer, and then is the deformation. And the deviation in the experiment maybe is the might be gap between the tennis ball and the friction coefficient in different ball. And that is a parameter. Because due to the problem statement, we want to know the friction coefficient between the tennis ball and how does the top mass of the top ball change affect the structure, and what is the H ball per layer change affect the whole structure.
Okay, thanks. I think we can proceed with the discussion.
And may I use the blackboard? May I use the blackboard?
Okay.
And here's the tennis ball tower. Can you draw the direction of the friction in this tower and act on this ball? The direction of the friction.
Actually, we think like the first layer is basically like the
I mean this layer, this ball.
this layer,
Yes.
this ball.
Yes. How will the friction affect this ball?
Like this ball, we think that's the second layer is the inward friction, and this layer is this layer, the outward friction.
And this ball didn't get the friction to support this ball will not get. So can you mention that again?
You said this ball or this ball?
And so can you hold the friction on this ball?
On this ball?
Yes.
Well, this ball really is for the inward friction, and also this ball is for this outward.
Did you agree with this ball will also give the inward friction like this?
Yes, I agree.
So according to that, can you explain what is the including angle between this? Because it is a 3 dimension, so you need to consider this angle that you mentioned in the theory.
This angle.
Yes. Also, okay. Please turn to page 7. Page 17. The theory shows that the N1% theta will equal to 1 divided by 3 mass of the top ball. Don't you think that the vertical component of the friction will support the mass of the top tennis ball? Friction will also support.
Left plus. I mean, this box engine will divide into 3 balls.
Yes, but the opponent thinks that the friction will give the direction like this, and it has a vertical component and a horizontal component like this. Did you agree? So
Yeah.
I think the theory should consider the friction like this. Did you agree?
Yeah. But we only mentioned energy, not friction.
But
In the first part.
And you mentioned that. Please turn to page 21. And you said that there is no limitation in this page, but as for in your short question you asked there.
That's my wrong. I'm wrong.
Okay, so okay. And the friction will increase or decrease as the layer is increased.
The layer is increased, the friction will increase.
And if you set a pivot on here, this friction will in your theory it says that this friction will be bigger than this friction, right?
Yes.
But when you set a pivot in here, the torque of this is not be equal. So in your theory, the ball in there will rotate.
Yes, we know, but we think that's what we thought, but we don't know why it is not equal.
Okay, but it's because the included angle is not the same. So when the normal force is increased as the layer is increasing, so the friction will increase too. In order to balance the horizontal component, do you agree with it?
Yes, I agree with you.
And so can you predict so please turn to page experiment that measure the friction coefficient. So how did you measure it? how did you measure the friction coefficient?
Page one.
Yes, how did you measure you?
We measure it by the angle we measure. Like when it will slide down, and we measure the angle.
Angle between this.
Yeah.
The opponent thinks that, which do you agree that tangent theta?
Yeah.
Because tangent theta is when the tangent theta is bigger than 1.773, this degree will over 45 degrees. Do you agree?
Please repeat it.
When the tangent theta is equal to 1.73, this angle will bigger than 45 degrees. Did you agree? So
Yes.
so the opponent thinks that the measurement of this tennis ball will just fall it instead of sliding on it.
You mean it's
Well, we will just fall, not slide.
But we see that it's just like.
Okay, and please turn to page. So can you predict the gap between the tennis ball?
We didn't predict it because we only see them, but we don't know why. There is a gap between tennis, but it's just equal. It's just equal.
So don't you think that in your theory, compared to your theory and your experiment, did you think that your theory can explain the actual situation?
Sometimes we think our theory is not
correct.
not can all demonstrate the actual.
Opponent believes that in a theory you should consider every friction on this ball, and it will give the inward normal force. And did you agree that the normal force will give outward horizontal component?
Outward force.
Outward means out.
Outward force. Yeah.
And after you demonstrate it, you will find that your theory is wrong, so it cannot demonstrate all the situation. Did you agree with that?
We think that the gap is no force, so we can calculate the force.
So after we discuss the measurement of the friction coefficient on the tower, next I want to discuss about the whole tower. Is there any possible tennis ball tower can be said when different poles are there, and you can predict it?
Like different sports player.
Yes.
Yeah. You mean pots?
Different poles there.
And the pots.
Different. Can you predict how it happened and the real theory in your experiment?
We think that the higher tower is the less friction, the lower the layer has too small friction, so the tower will be unable.
Okay. As you mentioned in the short question, I will talk about deviation. You say that when air is more higher, the angle between this will increase, right?
Yes.
But when it is increased, it will like this. It's not fit with the real life.
It will increase.
Also, your answer wrong in the transcript. And so you think that which parameter is affect the stability of the tower the most?
Which parameters? We think that the friction between it affects the tower the most.
But you think.
And the higher the friction, the smaller the layer of the friction between the poles.
And so can you write again what is the top layer? What is the actual situation compared to your theory and your experiment with friction?
Repeat it again.
Can you compare your theory and the experiment in your theory? how did you verify your theory is wrong? Is right?
Because we can see that the higher the layer and the smaller the nuance of the first layer.
In this theory, did you agree with the normal force will proportional to a friction?
Okay, time's up.
No, we don't agree.
I think the opponent should summarize his discussion in 1 minute.
And first, we talk about the force analysis, which including the theory in the for the reporter didn't consider the vertical components of the friction that supported to the mass of the top bone. And the friction part, he said the direction of the friction is inward, but the reporter says that the friction will differentiate as the ball. But when we said that the pivot at the center of ball, the theory is wrong, and we talk about the deviation between the gap between the tensile and the gap. So, and how does it affect the friction coefficient? And comes to the structure. The reporter also can describe what is the actual theory in H bar per layer and amount of layer.
Okay, time's up. I think let's take the reviewer to ask a question for 3 minutes.
Okay, so question for the reporter. Do you think there is any way to block the influence of the external
Let's say it's louder.
is there any way to block the influence of external factors?
External factors. Like what?
Next question. How do you make sure every tennis ball in the same layer have the same coefficient of friction?
Yes.
Okay, measure it. And do you think what is the factor that restricts tennis from continuing to increase the number of layers?
Let's repeat it again.
What is the factor that restricts the tennis from continuing to increase the number of layers?
Torque.
And so, question for our opponent, what do you think is the restrict tennis will continue to increase the number?
You said the friction will increase as the increasing of layer, or friction restrict, or
Restrict to continue increase the layer.
I think the friction coefficient will affect this situation and restrict the layer of the tower.
Okay, so question for reporter, do you consider different frictions of the floor?
Yes, we have considered it.
So, question for reporter, what is the angle that you hit the ball? How do quantitatively measure the strength of the force when you hit the ball tower?
So when we hit the
ball tower.
when we hit the bar with tower, we didn't measure it.
Oh, so maybe you can try to hit the ball tower to test its stability. So, question for reporter, how do you stack the balls? Is it accurate to stack by hand?
Stack by hand.
How do you stack the balls?
How do I stand the ball? We just stand the ball by our hand and not use too much force.
Do you think it's accurate to stack by your hand?
Well, it's not easy, but we try it several times.
So, what do you think the way you can stack the balls and make it accurate?
We can use a 3D model. We can create a 3D model that fits the shape of the tensile tower to stack it instead of use the hand to stack the tensile.
Okay, I agree with the opponent. And you have mentioned that if the layer becomes higher, the friction will become higher.
Okay, time's up. I think the reviewer can take 2 minutes for preparation. Okay. I think the reviewer finished to her presentation.
Hello everyone, my name is Bei and I'm the reviewer from Team Charlotte at Jinchen High School. So I'm reviewing problem number 6, tennis ball tower. And here's the main focus in our reviewer view and how high can the destroyed structure be stacked in an experiment before it collapses, and what gives the tower its stability, and how does the construction of the tower affect its stability, what other parameters does it depend on, and are towers of more than 3 poles more stable or unstable? And this is a summary for the report. First, the understanding of the problems. So we think they consider the gap between the poles on the same layer, and they think there is no friction force, and they focus on the normal force and friction force. And for the theoretical analysis, they use the Newton's third laws, and they think the action equals the reaction, and for the friction coefficient affects the stability. And for the experimental confirmation, it is in the different force for different layers, and they discuss the relationship between the stability and the layers of the tower. And they talk about when taking off the top tennis, it falls layer by layer. And this is the pros and cons for the reporter. So for the pros, we think they have clear introduction to the problem and observation video, and they use Newton's third law friction coefficient to quantify the result, and their experiments to verify the theory regarding Newton's third law's first analysis degree of inclination and deformation. And their concepts on clear analysis, and we think they need more discussion on the experimentation and theory. And they did not consider the boundary condition, normal force on the same layer. And here's a summary of the opponent. And the key insight of the opponent is they need no more discussion comparison between the theory and the experimental data. And they think the opponent enough physical explanation based on the clear theory. So here's the pros and cons for opponent. We think the opponent has a clear questions and directly fits the report, and we think they understand the experiment well, and we think they have sufficient use of opposition time, and they legitimate question asks on further understanding of the theory, and that they have sufficient use of and the cons for the opponent, they are lack of comment on the reporter, and they do not focus on what the reporter say and do not let the reporter speak completely. So here's a discussion analysis. So first, the opponent asks what's the direction of the friction, and reporter's response is right on the blackboard, and we agree with the opponent. And this is an opponent asks about vertical friction also affect, and reporter's response is no, it will not consider, and we agree with the opponent. And the opponent asks about layer increase when the friction decreases, when the friction decrease or increase, and the reporter's response is it will increase, and we agree with the reporter. And our opponent asked for how to measure the friction coefficient, and reporter response we didn't get a clear answer, and we agree with the opponent. And for the next question, they asked can the theory and the experiment fit, and reporter response is not always right. They in some situation they cannot fit, and the opponent thinks they have to fix their theory to fit the real situation. So they asked about which parameter affect the result of the most, and reporter's response is coefficient of force. The friction has positive correlation with the layer, and we agree with the opponent. And here's a reviewer's question. What is the factor of leveraging the tennis to continue to increase the number of layers? And opponent says
Okay, thanks.
Thanks for your kind attention.
I think the last concluding remarks from the reporter, 2 minutes. The reporter.
In the same layer, so there is no force between them. And also in our experiments, the balls in the same layer didn't contact each other, so there is no end. And the higher the tower is, although n is bigger, but the mu s is smaller, hopefully the less friction it has. So too small friction so tower will be unable. So we will move the plate slowly to measure the friction of every materials. And the cable's μs would affect the head limits of the tower. And also when the vertical direct past the function, and its work will not affect the torque. And okay. Thank you.
Okay. Give time for the question for the jury. Anyone?
Yes, I have a question for both reporter and opponent. What is your definition, theoretical definition for the stability? For the reporter first. Yeah. And then,
We think the stability is related to the friction and also
yes. Do you have any kind of experimental way to calculate it or to determine that?
we think that the higher layer, the μs will become smaller, and also the friction will become smaller. So if the torque will not be stable, yeah.
I think the definition for the stability must like a transporter is not collapsed for 30 seconds. It is the clear definition for the stability.
Okay, I think if there's no question, I think it's just a mark.
Sorry. Yeah. So I would like to ask the three of you that to answer that if I choose the different substrate, okay, the ground, how will it affect if I choose the rock or smooth? What do you think will affect your result or not? Okay, maybe start from the reviewer and the opponent and the reporter.
I think maybe you choose a more rock floor, and you can build a higher layer of the technical tower, because the friction coefficient of the floor may affect the layer of the technical tower.
I think if you use the smooth surface between the table and the tennis ball, it has less friction coefficient. So the tennis ball tire will collapse. If we don't bigger than the series says, so it will collapse. And if we choose the friction coefficient is bigger, it can affect its stability and make the tennis ball tire not to collapse.
We think it is related to the μs. If you choose too smooth materials, and then the friction will not enough to make the car be stable.
Thank you.
Anyone? Okay. Let's take the marking time. Let's wait for 1 mark. for the reporter. Okay, 6, 5, 6, 6, 6. For the opponent. Okay, 7, 6, 7, 7, 6. For the reviewer. 7, 6, 6, 6, 5. So I think it's rather average thing. We don't need to include your comments. So we can take, I think, 10 minutes break. Okay, you can start anytime.
On to challenge of number 7, please study that.
The problem number 7. 3 slice dice. So 1 minute to start. Okay, accept or reject? Accept, okay. And then you can take 5 minutes of preparation. In the meantime, everybody please write down your name on the platform. Okay, let's see the important presentation.
Honorable Juries and fellow competitors, I'm the reporter from Team Excelsior, and the problem I'm going to report is the three-sided dice. And this is the problem statement. To land a coin on its side is often associated with the idea of its rare occurrence. What should be the physical and geometrical characteristic of a cylindrical dice so that it has the same probability to land on its side and one of its faces? And we mainly focus on when does the dice have the same probability to land whether on length or on face? And how does the relevant parameters affect the probability while landing? And this is the outline of our report. First, I'm going to show you my preliminary experiment, and then our theoretical model, and also our experiment and discussion, and last will be our conclusion. And first is the preliminary experiment. So, but in the observation video, you can see that when the dice drops, it will first rotate in the air. Then after it bounces, it again bounce up and rotates in the air again. And which side it will land on depends on the last collision with the dice of the dice and the surface. And next, I'm going to talk about our theoretical model. So first is the calculation of moment of inertia. So we can know the moment of inertia in the three axes, but the two rotation axes that will affect the landing of the dice is the x and y axis. So we can focus on these two. And so after because we knew that, and also after the dice drop on the surface, the rotating axis of it is still parallel to each other. So we can use the parallel axis theorem to calculate the moment of inertia of the whole dice, which will be like this. And next, I'm going to talk about our analysis of the torque, and this is for the sliding situation. In a sliding situation, the pivot of the dice will be the centroid of the dice, and there will be two forces that is mainly affecting the dice, which will be the friction and the normal force. And because the direction of the sliding cannot be predicted, so the friction of the dice remains unknown. So when we are calculating the torque, you can see this. It is because the direction is unknown. So when we calculate the torque, we can add the torque of the normal force and the friction together, and this will be the torque of the whole dice. And next is the analysis of the torque in a stock situation. In this situation, the pivot of the dice will be here. And so we can know the coordination of this place, which will be like this. And then we can know the acceleration of this point, and it will be like this. And then we can also use these two to calculate the torque of the dice, and it will look like this. And next is the geometrical model of a fair three-sided dice. So we assume that when there will be an imaginary sphere around the dice, and which will look like this. And this sphere can be separated into three parts. First part is here, second part is here, and last part is here. And we assume that when the surface area of each part is the same, the possibility to land on each faces will also be the same. So since we know the radius of this imaginary sphere, we can know that the surface area of each part should be like this. And while this equals to this, which will be the surface area of this part, we assume that it will be a fair three-sided dice. And so after calculating, we can know the aspect ratio for this geometrical model should be 1/2. And next, I'm going to talk about our experiment. And we use an acrylic cylinder as our dice, and we use a releasing apparatus to release our dice. And the reason we use a releasing apparatus is because we want to control the initial velocity of the dice dropping. And so this is our first experiment about the radius of the cylinder, and we measure the probability to land on each faces, so we can use the accuracy of our geometrical model. And we control our thickness of the cylinder to be 0.7 centimeters, and our sample size is 600 times. So you can see in our result, when the radius of the cylinder increases, the possibility to land on the edge will decrease, but the possibility to land on the face and tail will increase. And you can see here, when the radius of the cylinder is 1 centimeter, it has the same probability to land on each side. And so we can know that when the thickness of the dice is 0.7 centimeters, the radius of the dice should be 1 centimeter, so that it could the dice will be a fair three-sided dice. And you can see that the ratio of it will be 0.7, and which is approximately 1 square root 2, which is the result of our geometrical model. And next, I'm going to talk about the analysis of the characteristics for the same probability. In this graph, you can see that in these 5 conditions, the probability to land on edge is about 33%. And if we put this in this graph and we fit a line into it, we can see that the slope of the line will be this 0.7249. And this will also be the ratio of the thickness and the radius of a three-sided dice. And this is also approximately same to 1 square root 2, which is our geometrical model. And next, I'm going to talk about our discussion. So first is the discussion about the limits of releasing height. So we define the condition random when the rebounding height of the dice is bigger than the radius of our imaginary sphere, which is because that when in this condition, it will have enough space for the dice to rotate after it collides on the ground. So it looks like this. When the dice drop onto the ground, it will bounce up and it rotates in the air. And so the radius of the sphere looks like this. And so we can know that when the rebounding height of the dice is bigger than the radius of our imaginary sphere, the dice will be in a random situation. And so by calculating the relation between the releasing height and rebounding height, we can get the limits of releasing height. So when it is in I'm going to explain when the dice is in a non-random situation. So in this kind of condition, the dice will drop to the ground, but it will not be able to rotate. And so it will become a stuck situation here, and the pivot will be here. So we can draw a normal line from the pivot like this. And when the centroid of the dice is on the left of the pivot, it will fall to the left. And when the centroid of the dice is on the right of the pivot, it will fall to the right. And we can see that in this kind of condition, the landing of the dice will be influenced a lot by the initial condition. Therefore, we define this as a non-random condition. And this is our experiment about the limits of releasing height. And we measure the boundary condition of random and non-random. So you can see in our result, when the releasing height is 1 centimeter, we did this experiment with a fair three-sided dice, and we released it with the face facing on top. So we can see when the releasing height is 1 centimeter, the possibility to land on faces is 100%. But as the releasing height increases, the possibility goes more and more even. And so we can see when the possibility is bigger than, so when the releasing height is bigger than 1.82, the possibility to land on each side will be more and more, it will be approximately the same, and so we call it a random situation. And so it is because that in this condition, the possibility to land on the which faces will be too much influenced by the initial condition. And so we can get that when the releasing height is bigger than this, it will be a random situation. And we also did an experiment we used a bare three-sided dice and released it with a face on top, tail on top, and edge on top. And you can see that it all have a similar boundary about the releasing height. And this can prove that when the releasing height is high enough, the landing side of the dice will not be affected by its initial condition. And by these 3 experiments, we can also know that our theory can fit in every kind of initial conditions. And last is a discussion about the coefficient of restitution, and our parameters is the different property of surface, and we also measure the condition of random and non-random. And so we can calculate the coefficient of restitution by measuring the initial height and rebounding height of an acrylic ball. And this is the result, and these are the materials we use as our surface. So we can see in the result is that when the coefficient of restitution increases, the limit of releasing height decreases. And this is because that when the coefficient of restitution increases, the random situation will be more easier to achieve. And it also fits with our formula, which is this, and it means that when the coefficient of restitution increases, the limits of releasing height decreases. And last, I'm going to talk about our conclusion. So this is the conclusion of our geometrical model. So we assume that when the surface area of each part of the dice is the same, the possibility to land on each side will also be the same. So we can calculate, and so the surface area of each part should be like this. And after calculating, we can get the aspect ratio for this geometry model, which is 1√2. And we have proved it with our experiment, which is that when the radius of the dice is 1 centimeter, the height of the dice should be 0.7 centimeter, so that it has the same probability to land on each faces. And the aspect ratio of it is 0.7 and fits with our theory. And this is the conclusion of our releasing height. We get this formula which is about the limits of releasing height, and it is because that when the rebounding height is higher than the radius of the imaginary sphere, the dice will be able to rotate in the air and cause the random situation. And the last conclusion is about our coefficient of restitution. We can know that when our coefficient of restitution increases, our limit of releasing height decreases. And this is because that when the coefficient of restitution increases, it will be more easier to achieve a random situation. So we can see it fits with our formula, which is that when the coefficient of restitution increases, the limit of height decreases. And this is my report. Thank you.
Okay, the opponent to ask questions.
Thanks for reporter's report. And I first want to ask, do you consider air resistance?
No.
Okay. And how do you roll your dice?
You have mentioned that you use the machine, but
How does it actually release the
it just this breaker just open and the dice will fall. So it is a free fall method. So it just fall with no initial velocity.
Okay, thank you. And so, is there a fixed side down when you throw your dice?
Yes.
Okay, and what do you create a real dice, or you just use the theory?
We use the acrylic cylinder to be our dice, and this is a real dice.
So, what is the material of your dice?
Acrylic.
Okay, and so how do you measure the angle between the table and the dice?
We did not measure it.
Okay, and so
because our random situation depends on the height of releasing, so we do not have to measure the angle between the surface and the dice. Yes.
okay, so how many times do you use the same dice?
How many times? We have like a lot of dice throwing in the same time. So how many times for each dice? Like approximately 15 times.
Okay. Okay, and that's all of my questions. Thank you.
Thank you.
Okay, the opponent takes 2 minutes to prepare. Okay, the opponent takes the floor.
Hello everyone, my name is Diana and I'm from Kingston High School, Team Data. And today I'm going to propose problem number 7, three-sided dice. So here's the problem statement. To land a coin on the side is often associated with the idea of a currency. What should be the physical and practical characteristics of a cylindrical dice so that it has the same probability to land on its side and one of its faces? For the main focus, we focus on can you estimate the optimal cylinder for this, and for the theoretical consideration, it must be considered at which side the object comes to raise depending on both the solid angles when it hits. A simulation that tries out different angles is built for this. So this is the structure of the reporter. For the observation part, they give the clear video and they tell us that the last collision of the dice. For the theoretical model, they focus on the moment on inertia on 3 axes, and they told us that only the x and y axis will affect the motion. For the torque, they use parallel axis theory to calculate, and they also give a geometrical model showing. Okay, for the setup, they control the initial angular velocity with the currency device, and they focus on the sliding situation and stroke situation. For the implementation part, they focus on the radius of the cylinder, define the random and limit resisting height. And they also give us, they get the ratio of the three-sided dice is 1/√2. For the conclusion, they tell us that the motion will affect by a lot by the initial condition. And this is a strong and weak point for a reporter. First, for the strong part, they gave us the introduction to a problem and observable video. Also, they use moment of inertia to quantify on the result and their experiments to verify the theory regarding the ground and rotation. Also, they get the accuracy of the device initial angular velocity and coefficient of restitution. For the weak part, I think they missed that they didn't consider a resistance, and they didn't consider the friction coefficient and coefficient of elasticity, and they also lack of investigation on rebound and dismantle. So this is the questions and discussion I want to discuss later. First, what is the area of each side of the dice? Do you think that the sectional area is small enough to ignore the effect of air resistance, and how big is the effect of air resistance? How to solve it? And how do you roll your dice? Do you flip your dice, or how have you tried many ways, and how is it associated with the result? Also, will a surface affect the environmental result? Also, will dice rebound after falling, and how will it affect the probability? Is the elastic coefficient of each side the same? How is it associated with the result? And what are the different experimental results by changing the side down when you are throwing the dice initially? And will there be an initial velocity for the theory? Will different initial velocities affect time and rotation, or even lead to a different result? And we also want to ask that, are you sure that each side has the same probability? Is your data enough to prove that? In the end, we'll ask, have you considered the coefficient of friction, and how will it affect the experimental results? And I think we can move on to a discussion part. Okay, and first, I want to ask, what is the area of each side of the dice? So here we assume that there will be an imaginary sphere of around the dice, and so there will be 3 areas, which is this area, and this area. And we assume that when the surface area of these 3 areas is the same, the possibility to land on each side will also be the same.
I want to ask is that is the sectional area is small enough so you can ignore the air resistance?
Do you mean this?
Yes, the sectional area. Because in our opponent's view, we think that the air resistance may affect the time, and it will also affect the rotation, and in order to affect the probability.
Do you mean that if this will affect the probability of the dice?
if the area is small enough that you can ignore the air resistance.
Oh no.
So in our approach view, I think we should also take air resistance into consideration.
But because our the landing at last depends on the last collision with of the dice and the surface. So in the last collision there will be no the air drag will not. The last collision will not be caused by the air drag. So we don't think that will affect our experiment results.
But will air resistance affect its rotation, which means when it falls down, there will be different side. So that will affect the probability.
The rotation. But because we set this to be a random situation, so if we consider too many, it will not be a random situation because the problem statement has asked for a random situation.
Okay, I want to move on to another question. I want to ask, will the dice rebound after falling? Will the dice rebound after falling?
Yes, it will, and it is also how we define the random and non-random situation. We define that when the rebounding height is higher than the the radius of imaginary sphere, the condition will be random. So yes, of course it will.
I want to ask, how big is the effect of the rebound?
How big? If it doesn't rebound, the initial condition will affect the result very much. So the rebound is very important. And also, you can see that when here if coefficient of restitution can decide that how much it will rebound, and so you can see that when the coefficient of the restitution increases, the limit of releasing height decreases. So yes, it affects a lot, and we did an experiment about it. And
in our opponent's view, I think that the rebound will affect the path of the dice after rebounding, and
we also think that only the last rebound of the dice will affect the result.
so have you considered the probability after rebound?
Yes, as we mentioned in our report, so can you repeat your question?
Have you considered the probability after your rebound?
Probability after. Do you mean that the probability difference between that it didn't rebound and it did rebound?
I mean, could you consider the situation after the rebound?
Yes. After it rebounds, we said that when the rebounding height is higher than the radius of the imaginary sphere, the dice will be able to rotate in the air. And when it rotates in the air, it will change the possibility to land. It will change the side it will land up. So yes, we did consider it.
Okay, and we can move on to another question. You say that you control the same side when you roll a dice, and I want to ask, what do you think the result will be different when you change the side down when you roll a dice?
So we can see here the limit of releasing height, because when the you can see that we do 3 different experiments, which is the face on top, tail on top, and edge on top. And while the releasing height of the dice is high enough, the possibility to land on each side will be the same. But when the releasing height of the dice is too low, the probability to land on each side will be affected a lot by the initial condition. So this is why we did the experiment of the limit of releasing height.
In our opponent's view, that I think the different elasticity coefficient of each side will affect the motion. And I want to ask that, is the elasticity coefficient of each side the same?
Yes.
Okay. So we side has the same probability? Is your data enough to prove that?
So I did mention in my report that the sample size of our experiment is 600 times, and which is yes, here. Here, our sample size is 600 times.
Okay, but I think 600 times cannot be enough for proof that the probability of each side is the same. So I think you should still do more time for measurement to prove the probability is the same.
But we have a geometrical model for it, so we think that because our geometrical model fits with our experiment, so we think it is right, and we think 600 times is enough for it.
Okay, thank you. And we can move on to another discussion. Have you considered the coefficient of friction of the?
Yes. Actually, we don't have to consider it because we think it does not affect the result.
But in our opponent's view, I think that it will affect the rebound.
In our opinion, we think that the only thing that affects when the dice stucks here, you can see that we drew a normal line, and in this situation, when the centroid of the dice is in the left, it falls onto the left, and when it is in the right, it falls onto the right. And this happens in all the last bounce of the dice, and it does not have to, the friction does not have to be considered into this situation.
So do you think that the friction will affect the rebound?
Rebound?
Because the force will be different, and maybe it will make the motion of the dice different and change its path.
But the friction only affects when the dice is in a sliding situation. But and it does not affect when it is in a stuck or bouncing situation.
And I want to ask that how many times will the dice rebound?
We cannot predict it.
Can you explain that with your experimental data?
Because we don't need to know about how many times it rebounds, because we have mentioned that only the last collision between the dice and the surface will affect the results. So we do not have to consider how many times it has rebounded in the before the last bounce.
But after the rebound, the phase that falls down in the end may change, because the little force that makes the dice rebound, and it will just rotating and it will fall down.
Yes, so it may rebound a lot of times, but only the last bounce will affect. Only the last bounce will affect the result.
Okay.
Okay, time out. I think the opponents just summarize the discussion.
First, we have discussed that if the sectional area is small enough for the reporter to ignore the earth's resistance, and she said that she just ignored it. And for rebound, we have discussed a lot. In our opponent's view now, I think that the rebound will affect the probability a lot, but the reporter mentioned that only the final contact will affect the motion, so they do not focus on that part too much. And I have asked that is there experimental data enough to prove that the size has the same probability? And they say that they just do 600 times, and that is enough to prove that the probability is the same.
Okay.
Thank you.
The reviewer, the last question.
Reporting and opinion. And our first question is about reporting. And what did you define around this situation?
When the releasing height is over our when the releasing height. Huh?
2 centimeters.
No. It depends on the coefficient of restitution and also the yes, it depends on the coefficient of restitution.
For your opponent,
Can you say
what did you how did you define around this situation?
you can draw a dice many times and you see that
Many times.
many-
Times. How many times?
yeah.
Define this situation. Very nice. What's the most important parameter?
Parameter. I think
No, thank you. My next question is for the party. How did you define the last round?
the last collision of the dice and the surface. Yes.
How did you define the last round?
it's because it
May not refine just read some.
Okay, so the last bounce is when the rebounding height is lower than the radius of the rotating the radius of the imaginary sphere. Because in this condition, it will no longer rotate and affect the
No longer repeat. No longer repeat.
Sorry, can you rephrase your question?
Sorry, I want to. For recording, did you think the softness of the contact surface would affect the result?
You mean the friction of the contact surface?
Softness.
Softness. Well, this can be affected by the coefficient. This can affect the coefficient of restitution. So yes, it will affect, and we have did the experiment.
can you say this one again?
Did you think the softness of the contact surface will affect the result?
Yes, I think it will affect the result a lot and it don't cause the rebound of the dice.
And for the party, did you think the different initial conditions will affect the result?
When the releasing height is high enough, you can see here.
The most is the releasing height. The most affect the result is the releasing height. The initial condition.
Whether it will be random depends on the releasing height and the rebounding height.
Okay. I think the review will take 2 minutes to prepare. Presentation. Okay, I think we want to take the floor to present.
Reconnect. You have to unplug and plug in again.
Patents are one of the reviewers from television. My name is Yu. I'm going to review the problem number 7, 3-sided dice. And test a problem statement to land a coin on the side is often associated with the idea of a real occurrence, what should be the physical and geometrical characteristics of a cylindrical die so that it has the same probability to land on the side and one of its faces. So I think I should mainly focus when this is what's the dimension of a fair cylindrical die. And this is the overview of the reported. First, for her observation, he showed a video. In the video, the dice and food are the same thing. And in the tertiary, she used the movement of inertia on the turret, sliding and stack analysis, and the coefficient of restitution. And in her experiment, he controlled the radius of the cylinder, and she done different material of the contact surface, and she done different the releasing height. And for the advantage for the reported, she has theory of illustration and modeling. And my suggestion is she didn't do the experiment to prove when she chose 600 times it would be a remnant situation. And now review of the opinion. She has a brief overview of the presentation. The reviewer has some suggestions as she is focused on the standpoint to learn. And in the discussion, does the softness affect the result? And both answers yes, opponent yes. And the reviewer believes that, and yes, it is. I agree with those. I think the softness of the contact surface can decrease the kinetic energy of the cylinder so that it can reach the last condition. And in the last condition, the result depends on the relative position of the various contact here. And I asked, how did you define the last beyond? And before say the bonding, the last beyond is knowing only vacation. And so there's some points. I think our research might affect the results because their size.
Okay.
Their size.
Lastly, let's reporter to make concluding remarks.
Okay, so in our report, I have calculated the moment of inertia, and we have analyzed the torque of the three-sided dice, which include the sliding and stack situation. And we have laid a dice in a random situation, which is defined by the flapping height, and we also find the best geometrical model that can fit with our experiment. And we have discussed about the limit of releasing height, which affects the random or non-random, and we analyze the coefficient of restitution and see how it affects our probability. And these are the remarks. And first, we have controlled the initial velocity and control it without the angular velocity, but it is still a random condition since that we have defined it as the by the releasing height. And we have considered the friction of coefficient, and it does not affect the result. And assuming the dice is a rigid body will not affect the result too. And when the releasing height is high enough, the initial condition cannot affect the result. And because and all of the experience data are considered a dice which is in a rebounding situation, and we believe that 600 times of experience is already very enough. And only the last rebound will affect the result, and so the rebounding times before the last rebound does not affect the result of the landing side of the dice. And the thickness of the dice only affects the probability, which it is random. So the thickness of the dice can affect whether the probability of the dice, but it does not affect whether it is random, since that this is defined by the releasing height, and we also have our experiment to prove it. And the angle does not affect the probability in a random situation, since if the height is high enough, it doesn't affect.
Any questions on the jury?
I have a short question for reporter. How to define your boundary line 1.82 in your figures? It depends on your size, or I don't know.
We
Can you explain why is 1.82?
This 1.82 is here. So when the releasing height is higher than this, so the 1.82 is calculated by this formula, and when the releasing height is higher than this formula, it is in a random situation.
Okay, I have a question for the reporter. Do you think if the initial velocity increase will affect your result or not?
We think it will not, because...
Okay, thank you. Not right. So I would like to check the opponent. Do you think the air resistance will affect the possibility?
Yes, because we think that it may make the time that the dice stay in the air longer. So it will make the rotation for the dice more unstable.
Okay.
Okay, I have a question for all. How do you throw a dice randomly?
We didn't throw.
Well, don't just ordinarily. How do you throw a dice randomly?
With our hands.
Yes.
Yes, but because
how do you do this?
how do we toss a dice randomly? We use our hands to toss it and like throw it up, or just simply put it up.
Okay. Well,
I think. I'm sorry, can you repeat the question again?
just how do you throw a dice randomly? If someone asks you to throw a dice randomly, how do
We
you do it?
flip it, or we just throw it in an unstable way.
Okay.
I think we can use a card and shuffle the dice and throw the dice. And I think the random situation is not just depends on the releasing height.
Okay.
Also the inertial condition.
Okay. I think question is over. I think let's consider for the mark. for the reporter. 7, 7, 8, 8, 8. For the opponent. 7, 5, 7, 6, 6. For the reviewer. 5, 6, 5, 5, 6. So this ends the second session. I think we'll be back 10 minutes later. Okay, what's the problem?
We want to solve problem number 8.
Problem number 8. Repeat potential lines. So the reporter has 1 minute to respond. Okay, Chad. You have 5 minutes for preparation. In the meantime, please send somebody to write down the name of the presenter on the blackboard. reporter should report on the problem number 8, equipotential lines. Okay, now.
Hi, I'm Ray, and today we're talking about the problem number 8, equipotential lines from Chilzeta Typt High School. And here's the problem statement. So place 2 electrodes into water, supply a safe voltage, and use a voltmeter to determine the electric potential at various locations. Investigate how the measured equipotential lines diverge from your expectations for different conditions and liquids. So we'll try to main focus on the reason for the equipotential lines deviation and how different parameters will affect the equipotential lines. And here's the outline. So we're talking about observation first, and it's our theory, and the next will be experimentation and the conclusion. And here's the observation video, so you can see this text, the different value of the digital manometer, and just write it down on the graph paper and line it up. And so here's the introduction. So the first available parameters we'll do is about the concentration of the liquid, and the second will be the strong and weak electrolyte, and the third one will be our settling time of our experiment. And here the equipotential lines will be measured by the voltmeter and mapped on the graph paper, and also we will use the Excel to analyze the equipotential lines. And also our expectation of the equipotential lines will be symmetric, and the deviation we think is about the velocity of the ions. And let's talk about the theory part. So first we have to know about the electric potential. So we consider a point charged as the positive Q move from A to B in an electric field that is E, and the work will go down like this. So you can see the F equals to QE, and also the work will be stored into the electric potential energy like the UV. And also the potential difference can be written like this. So we can just calculate that the potential difference will equals to the energy, potential energy, and divided by the Q. And here's the potential lines. Let's talk about the dot C. So we can see that the potential difference will be the same from A to B and from the A to C. So we can just find out another dot like the dot B and dot C and just line it up, so we can just create our potential lines. And also the potential lines will be perpendicular to the electric lines that was formed by the electric field. And let's talk about another theory about the double layer effect. So we can know that the double layer effect will happen in the micro range, but we think we can still use this theory because this is talking about the line chain. And so what is the double layer effect talking about is about the ions when we close to the two electrodes, there will be more ions. And also you can see the potential will change like this. The potential will change in intensity near the two electrodes. And let's see about the formula. So we can see that the concentration will change about to the aerial change density. So we'll focus on the change of the concentration and the change of charge density, because the if the charge density is higher, that means the amount of iron is more higher. And the second will be the fixed law. So let's watch the fixed law in the first. So you can see that in two-dimensional, the gradient of the concentration will be proportional to the diffusive flux. So what we think that the diffusive flux, if the diffusive flux is higher, that means the ions will be faster. And also the second law we're talking about is the relationship between the concentration and the time. So I think that's the reason why the concentration will the potential lines will not be symmetric. It's because the concentration will move. So because we cannot measure each dot at the same time, and so that's why because the potential line is not symmetric. And the theory is talking about the simulation of the potential lines. So you can see D is the distance of the two electrons, and X is the distance to each of the electrons. And we can just written like this, and so you can see the K2 divided by the D minus X, and the K2 divided by X will be the electric fields, and we can just calculate it, and we can just change like this. And we can just insert the D and X, so we can just know another, that's the C, and we can use this C to simulate our diffusion lines. And also we can just see at the surface, so also the R1 and R2 will be the distance to the two electrodes, and so we can also just calculate, and we can know another C, and you just can create the diffusion lines. And here's the theory plot, so we can see at the left side is the line and right side is the surface. So we use this formula, and we also can know that close to the electrode and the higher voltage change will be. And we think it's because iron just like the double layer we have talked about, and also the right one will be a symmetric distribution, and that's just why the explanation of our experimentation. And so let's start about the experimentation. So first we talk about our equipment. So we will use the power supplier to offer the electricity, and we also use the digital multimeter to one probe of the digital multimeter in the circuit, and another side will let us to measure the voltage change. And also, so we use the carbon nails to be our electrodes, and also we use Excel and GeoGebra to analyze and to draw our extension lines. So we can just do about the water depth. So we can see we use the first theory formula that we draw the lines. You can see the theoretical line is also have higher in the beginning and lower in the end. And also we just think that the water depth will not influence the potential distribution, because you can see the line chain is fit in the surface and the end. And also the first experiment will be the different concentration. So we'll change the concentration and we'll control the voltage, that is about the 4 voltage, and we'll control the water depth, also the distance of the electrode, and also we'll control the temperature, and we'll change, so we can draw our exponential lines. So we have just known from the double layer effect that the concentration will change the aerial charge density. So we also just do the 1M, 0.1 M, 0.01 M. So here's the distribution of the potential lines. That's about the 0.01 M, and the whole voltage variation will be the 1 voltage, and the 0.1 will be the 1.5 voltage, and the 1 M will be the 1.6 voltage. And so let's look at the 0.1 M first. So the first we have measured from left to side. You can see that gradient near the two electrodes also will be more dense. And you can see the right side will be more denser, because we think that in the beginning of the reaction and the iron will move in not stable, so that might cause the concentration change higher and up. And that's why we can just see at the fixed law, the concentration will change the diffusive flux, and also it will change the amount of iron, and that can just cause the double layer effect phenomenon. And also, so we can just talk about some discussion. So the first one we can just discuss that if the concentration is higher and also the voltage direction will be higher, then we can just use the fixed first law to explain. And the third will be the concentration. The second will be the concentration will change with the time. And so that's the reason why we call it deviation, because we cannot measure each flux at the same time, and the concentration will just move every time. So that's the reason. And the second experiment will be the different electrolytes. So we just change the two electrolytes that's about liquid. We'll use the copper sulfate above the strong electrolyte, and the acetic acid to be the weak electrolyte. And so you can see the different electrolytes about the copper sulfate and the acetic acid. The left one will be the 1 voltage, and also the right one will be 1 voltage. So, but we can see just at the left side, the line is a little bit denser than the right side, because you can see the right side is about the symmetric. We think that's because the concentration of the liquid is lower, so we cannot just easy to see the difference about the potential lines deviation. So about the discussion, we'll talk about the strong electrolyte will dissociate more ions, and the group towards electrodes, and also okay, so that's close the two electrodes. Potential will be different, will be more obvious. So you can just see at the downside, the weak electrolyte will dissociate less iron, and also the strong electrolyte will dissociate more ions, and that will cause the concentration relatively will be not the same. So that's why the deviation of the equations will be more obvious. So the third experiment we're talking about the settling time. And you can see the deviation about the two acetic acid is about 1.8 volts and 0.94 volts. And you can see the left one is that the one we didn't put 1 hour, and the right one is the one we put 1 hour. So we think that is more lower variation is because you can see just in the whole system about the gradient of the potential. So if you put 1 hour of the reaction, and that means the ions will be more stable and will be balanced. So the concentration will be distributed more even. So that's why it calls the distribution of the potential lies more different to the left side, because the left side means the ions is still moving, so that will be not unstable, and that means the distribution of the efficiency will be more dense. So we can just discuss that if the time is, if you put more times, and that means the iron move will balance. So, but we think it won't be more symmetric is because it's also the same reason that we cannot measure each dot at the same time. And the second will be the time. If time is more time, the voltage variation will be lower, just because the iron of the distribution will be more similar.
Time's up.
We don't know.
The iron of the distribution of iron will be more not so dense. And so let's start with the conclusion. So the first reason of the non-symmetry with potential lines will be the concentration difference and also the velocity of the iron traveling. So and also the time passed. So let's see the Fick's law first. So you can see that the concentration gradient of the concentration will change the difference flux, and that will change the speed of the irons. And also, you can see the second one is about the water depth won't affect the voltage gradient because you can see we just feed our theoretical line. And the third one will be the settling time. If we set more time, and the distribution of the potential will be more symmetric, but now it will be in the whole symmetry because we cannot test each dot at the same time. So here are reference, and thank you for this in my report. Thank you.
Okay, question from the opponent. 2 minutes. Okay.
What do you mean with compound?
Some objects near the direction.
You mean another iron about effect?
Like hydrogen.
You mean the react near the electrode? Oh, well, that would be some effect, but I think so. We use the form. Yeah, okay.
The current with a stable result. Using the current with a stable result. The current.
Oh, you can see we just use the same voltage, so maybe the volt will influence, but we cannot see in our experimentation.
So you think the time with a stable result.
Yep.
If you change height, it to change the resistance of liquid, or why you change length?
I change height is because I think that you just talk about the resistance, so the amount of water will influence the resistance.
Do you think the different concentration of the same liquid is affect the line?
Yeah, I talked about the iron distribution will be relatively higher near to the electrode, so the distribution will be more dense.
So you see, and do you think the different liquid may affect the line?
You mean, yeah, just talking about the dissociate about the liquid.
Can you try to project 14?
Okay, time's up. I think the opponent should prepare for 3 minutes. Okay, preparation time for the approach is over. Please present your.
Greetings everyone, I'm your intern from Team Vision, and today I will report update on the opponent of the problem number 8 equipotential lines. And this is the problem statement. Place 2 electron into water, supply a set voltage, and use a voltmeter to determine electric potential at various locations. Investigate how the major equipotential lines deviate from your expectation for different conditions and liquids. And we may focus on the shape of the equipotential lines and the relevant parameters and its exploitation of equipotential lines. And it's the overview of the reporter. In his observation, she showed his experiment video. And in his experiment, he do the concentration of the liquids and the different electric and the settling time and the height of the water. And their analysis include electric potential and double layer effect, fixed laws of diffusion, and the theory deviation. And his conclusion is the water depth don't affect the results, and the concentration difference may affect the degree of the dissociation, and the settling time would affect the line because when it could modulate the concentration may be more stable. And it's the solution of opponent. And the advantage I want to get is to do relevant parameters and have nice demonstrate on the device and advanced results and clearly explain this phenomena data. And the solution I want to get him is the lack of the quantitative analysis and no theoretical and experimental comparison, and only quantitative analysis and did not will illustrate the experimental error. I want to have the discussion is the observation of its setup and container. And the parameters I want to discuss is the concentration of the liquids, the electron in different position, and the voltage and the current and the electric solution. And his analysis I want to discuss is the time and the voltage and the shape of line and the dynamic electricity and the permanence and the chemical reaction and the velocity of ions and the metal wire resistance. And the conclusion I want to discuss is the voltage affect the line and the different liquids and concentration of liquids affect the line. So I want to start my discussion.
Okay, we'll see with the discussion.
The blue line and the orange line have some difference, and I want to know what is the blue line and what is the orange line.
So first, I think that the digital multimeter will have some error because then we cannot measure it accurate more than the most accurate. So maybe just like a little bit. But you can see the line train is still the same. So I think that is.
I want to know what is the blue line.
Blue line is our one experiment I have to do. So we just show you the line that we have just example. For example.
The blue line is your experiment.
Yeah.
And the orange line is your
theoretical value.
Okay. Please turn to example. I want to know how do you draw the line? It seems like the distance is not as the same. The distance between 2 points.
So the first we have to choose the same axis about the electrode in two sides, and so we can just measure the same value of the potential difference and just line it up.
And the numbers means the number
means the voltage.
So how do you define the zero? The potential is zero.
No, you clearly still mean the digit 0.
Uh,
You mean the 0 part, and then the right side will be the 0 part, and the left side will be 4 voltage.
4 voltage.
Yeah.
And why didn't have a 4 voltage?
Oh, I think that would be some error about our creation about the electron.
So this picture has some error.
I mean just about the voltage level. We didn't write down the 4 voltage and 0 voltage, so maybe just like.
Where is your electrode?
We didn't double the electrode. We can just know at the 6th line and the 13th line and the 3. Yeah, so 3 and 6 and 13 and 6.
So the circle is around the electrode?
Yeah. Yeah.
Why the cubic surface is more elevated?
That's because it's a strong electrolyte, and that means
Why strong?
So strong electrolyte will dispose more ions, and I think that just can think about the double layers effect. So we can just know that the electrode will have more ions relatively, and that will cause the double layers effect. That is the distribution of the potential. The potential will just decrease in density.
And did you consider the gas like hydrogen was created near the electrode? If you use CH3COOH.
We didn't consider it.
But I think the permittivity of the gas have much difference from the liquids because the hydrogen's permittivity number is much bigger than the water. The permittivity is the number.
You mean the balance?
Okay. I think the gas have okay. And can you turn to page 70?
Need some deviation about the lines between the two. So I think it's just probably now as much about it.
Why you don't use more height? Higher.
I mean the limit of light is 1.2 centimeters, and we can just go higher.
So your electron only 1.4.
We have just used a small electrolyte mixed one.
Can you speak louder?
Maybe you can just do more hardware high, but we just do different hardware high from the initial just it's different 0.2 centimeters.
Can you explain your model of the equipotential line? Explain your model.
You mean
Because you said you have deviation, but you don't explain.
So the first deviation is because we expect our expectation
I want to ask is you have the expectation for equipotential line.
Yep.
And you know you have deviation.
Yes.
But do you compare deviation and explanation?
So you can see we use the formula have the theoretical, we have the symmetry.
You don't show it's not but can you turn to you draw the equipotential line?
You mean it's theoretical?
Yes, you have this theoretical line and your theoretical line has it considered the different liquids? So the line is in the phase it doesn't
Yeah, he didn't consider like this. He put about the like this.
And your model like static electricity. Your model is static electricity, but the experiment you do is the dynamic electricity, right?
You mean the voltage will change by the time?
No, I want to ask is, I think the dynamic electricity has difference from the difference from the static electricity. And can you explain why we can use dynamic electricity to explain the static electricity?
Can you just explain more?
And I think the line you draw is in the static electricity, right?
Yes.
The line you draw, yeah. But in this experiment, it's dynamic electricity because it has current.
Yeah.
So why you can use the static electricity to model your dynamic electricity?
We can measure the currents about the device.
No, I want to ask is why you can use dynamic electricity to explain the static electricity.
We think the huge one just clear. Maybe we just didn't consider it more clear.
I think we can use the dynamic electricity to model the static electricity because the way of ion's motion is from the positive electron to the negative electron, and it's similar to the electron from the high potential to a low potential. I won't ask it. I also want to ask why you choose for voltage to do this experiment.
So the high voltage will cause the reaction of the liquid will more intense. So because true voltage, we have to think that reaction will not influence more in our experiment.
So you think that use for is to decrease
Because
error?
in the 4 voltage we cannot see by in our eye that there are reactions, so we think that is can just try it on the 4 voltage.
Just use your eyes to check it.
Yeah, show the reaction about.
Did it have reaction?
I mean the reaction between the two electrodes have some bubbles near the
You
electrode.
don't see a bubble near
yeah,
the
yes.
electron, so you choose the forward.
Yes.
But I think it might have some error.
Yeah, so we just think the amount of bubble is not more just fine. A lot of
If it has the bubble, it changes a lot because the bubble is gas and you and it might have difference.
I can get your point. Thank you.
Okay, discussion is over. I think the opponent should summarize the discussion.
And according to our discussion, the reporter, I asked why report can use the static model to explain the dynamic electricity, and he didn't consider it. And I think the static. I think why we can use the dynamic electricity to model the static electricity is because the ion's motion is from the positive electron to the negative electron, and it's similar to the electron from the high potential to the lower potential. So we can use the dynamic electricity to model the static model because it's like this, the way it as the same.
Okay. Question from the viewers.
Okay,
3 minutes.
Okay, so reporter, you have mentioned that the deviation may caused by the measures, not accuracy, right?
Without a computation change.
So did you make sure that it is because that you measure not accurately, or you will have the deviation?
I think the main reason will be the computation change because if we use the weight meter and have the same, it's not a stable value of the yeah.
So for reporter, can you please turn to page 27? Have you analyzed the deviation? Did you analyze the deviation from your expectation? Means that theoretical equipotential line.
We didn't use the theoretical because we just can compare to kinds of electrolyte about the dissociation.
Okay, so and for the please turn to page problem 17. 17. And did you analyze the three dimension? Because you will have the
linear distribution.
Yes, you will have the thickness.
I think this will be a point that would be due in the future, but yeah, we can just do it in the 3 dimension.
Okay. So a question for the opponent. So what do you think that's the best way to quantify the deviation? What do you think the best way to analyze the deviation from the expectation?
I think it should consider the permittivity of the gas and our compound.
Okay, thank you. So for reporter, can you quantify the deviation?
I think it's pretty hard because we just can measure the.
Okay, thank you. So for the reporter, when two electrodes put into a pure water, will the phenomenon happen?
That would just it will happen, but yeah.
So for the reporter and the opponent, when the electrodes conductivity decrease, what do you think affect the deviation?
I think that might be the distribution of the electrons will be more dense.
Okay, so for the opponent.
I agree with the.
I think it's because the iron will move more faster and that will cause the.
Okay, next question. So for a reporter, if the two electrons is very close, what will happen?
The deviation will be more dense, I think.
Okay. So and so did you count for a reporter and an opponent? Do you think that the liquid temperature will affect the equipotential?
Yeah, the liquid temperature will influence the speed of the iron. Do you agree?
For the opponent.
Okay, time's up. I think the reviewer can take 2 minutes for the preparation.
Hello, the honorable jurors and fellow competitors. I'm the reviewer from the Excelsior. Now I'm going to review problem number 7, equipotential line. And the problem statement, place the two electrodes into water, supply the safe voltage, and use a voltmeter to determine the electric potential at the various locations. Investigate how the measured equipotential line deviates from your expectation for different conditions and liquids. This will mainly focus on the expected condition of the equipotential lines and how different liquids affect the equipotential line and why will cause the deviation. And this is the reporter outline. First, in the phenomenon, he shows the observation video and how they measure the equipotential line. And the theory part, he has the electric potential and the equipotential lines and doubles the caused by the double layers effects and use the Fick's law and the potential distribution. And in their experiment, they did some parameters about the concentration of liquid and the effects of the electrolytes and the settling times and the volutes. And this report's approach is about declare the demonstrations the equipotential line, but he can unclear the graph that didn't show the value or units of the axis. And clear that explain the deviation, but he didn't use the simulation to predict and he would, when you change the concentration, we change the density, also the viscosity at the same time. And have that of a comparison between the theory and the experiment means that due to the problem statement, the deviation. And this is the opponent summary. That's the first that he discussed some Fick's law and it's about the analysis of the times and the voltage. And about the opponent's pros and cons, the pros says he clarified the unclear graph of the reporter and point out the error and the deviation from the reporter. But he didn't discuss the boundary condition of the experiment, like the voltage of the voltage intensity and lack of personal input, and didn't ask about the theory limits due to their theoretical model, and didn't crush the aren't well structured. And this is the discussion about the deviation analysis. The opponent asked why is the theory lies different to the experiments, and they refer to ask about the deviation. The reviewer believes that you have the deviation caused by the sum of factors like the concentration, you affect the electrical conductivity of equipment, affect your measurement. And the second discussion is about the currents. They asked about the currents, but the reviewer said they didn't consider it. The reviewer believes that when the electrical potential difference will only cause the equipotential line, so maybe this will not affect the important points that need to be considered. And about the bubbles will affect that. The reviewer believes that the bubble will affect the resistance of the liquids, which will affect the measurements. And maybe this is the deviation, or this is the cause of the deviation. And also, opponent asks about consider gas, and opponent believes that the reporter should consider it, and also because it will affect some resistance or another factors. This is the promised in the discussion. Electrical parameters like liquids, electric conductivity, and the temperature, and didn't do an experiment about the electric shape, material, and radius. And the opponent believes that the reviewer believes that you will need to have a theoretical model to build a equipotential line, and also due to your experiment and have the deviation from your theoretical. So this is due to the problem statement. This is my review. Thank you.
The reporter, please make your concluding remarks.
So here's the remarks, and all in all, we have learned more about the Fick's phenomenon, and also I appreciate the opponent and the reviewer for the great discussion. So first we have the remarks will be the theory first. So we have talked about the double layer theory and the electrical Fick's first law, and also we discussed about the formula that has about the theory. So we think the opponent has access that the reason to use the static electric theory is because the ions will move between electrons, and like how iron moves in the static electric theory. So the point out we think that we can use, because I think that is because this expectation of this problem statement, and also the deviation will be not symmetric, and also about the implementation, the reviewers has and the opponents have said about the bubbles formed on the electron may somehow affect the experiment. And yeah, I agree with the bubbles will affect. So I think yeah. So and we just investigate the distribution in three-dimensional model. I think that's a great recommend because yeah, I just didn't simulate the three-dimensional model. And about discussion, so we have talked about the current can be ignored because the main deviation will be the potential difference. And also, yeah, we just talked about the deviation, and here is the remark. And thank you.
Okay. Question from Julie.
I have a question about your slide about the water depth versus the voltage. And it seems that in the middle locations, there's no deviation, but on the two ends, there are actually some deviations.
Because we think that near the two electrodes and the data we measure will be more unstable because yeah, the voltage will change in intensity.
Is it a randomly deviation, or is there any reason? Is there any trends on that deviation on two ends?
We use the middle as the zero because we think that the middle will be more stable.
Okay.
Short question for the forward. Please move to the page 13. You said that the blue line is done by the experiment, right?
This line?
Yes.
Yes.
Okay. The orange line is a theory line.
Yeah, theoretical line.
So how to using your theory line to approach to the experiment? Because I think your line is not correct.
You mean the theoretical line and the experimentation line?
It's a fitting line.
I think it's made by my feet, but just like I have said, there will be a measured error.
So you agree your line is correct?
I think the line is correct by by the measured error.
No problem.
Okay.
I would like to ask the reviewer, could you comment what is the most important thing or factor to cause the deviation?
I think the liquids, like the concentration and or the electricity conductivity, and also the
I mean, most.
the mode.
Yeah.
I think is the electricity conductivity.
Electricity. Conductivity.
Okay. Video. Okay. Let's wait for the mark. Okay. For the reporter. 6, 5, 7, 7, 6. For the opponent. 6, 5, 5, 5, 5. For the reviewer. 8, 7, 9, 7, 6. In this time, I think that's the applause for